So I did my project on the 2011 PHM Society Conference Data Challenge. My advisor was Dr. Chen. So I'm going to cover the problem, the data I was given, my solution, and the results. So the competition goal is they give you a bunch of wind sensor data, and you have to determine whether the wind sensor in a particular file is an error. And it's an error if it records a wind sensor measurement, that wind speed measurement that's more than 2% off from its actual value. In this particular situation, icing is not considered an error, and there are two setups. One is shear and one is pair. In the shear setup, there are 3 sensors at different altitudes, or there are 4 sensors at different altitudes. And in each situation, you have to determine whether one or more of the sensors is at fault. And with the pair, there are 2 sensors at the same altitude, and you have to determine which one of them is at fault or both of them are at fault. So there are 4 possibilities because each one can either be at fault or not. So, oopsie, I just discussed that. So they gave us a very small data set, which means it's something that can be analyzed in MATLAB relatively easily. All training data is nominal. However, it can have icing, and so that's how you train for icing. There's no, importantly, there's no training data that shows what a bad wind sensor looks like. The statistics are recorded over 10-minute intervals, and additionally, you can only submit 1 submission file every day, so that's another limitation. And they also don't give you the type of feedback they give you. They only tell you your ranking. They don't tell you how much you got right. So this is just to give you an idea of how much pair data they give you. And basically, they give you wind speed statistics, wind direction statistics, and temperature statistics. The only difference between shear and pair is obviously the number of files is slightly different, but also they give you the date for the shear files. But that's actually something I didn't use. So I have to state my assumptions. One of the assumptions I made is that the state is going to change gradually. So in other words, the weather is going to change gradually and predictably. And also, I made the assumption that the training data is going to change at the same predictable rate as the testing data. And I'm going to talk about how I refined that, and then obviously the sort of a necessary assumption is that errors of the same magnitude don't occur at the same time, because then you'd have a situation where it would just look like the wind dropped down in all the sensors, and so that's something I'm unable to predict, unable to sense. So I'm not going to talk about everything I tried, but I'm going to discuss a few things. One assumption I initially made, which turned out to be false, is that in the shear situation, first of all, in reality, in the real world, there is a wind gradient at different altitudes. At higher altitudes, the wind speed is going to tend to be greater. And so I thought I could use that in shear, but it turns out that the altitudes are low enough, all of them below 100 meters, that it's not something that can be used. Also, another assumption that doesn't work is that icing is going to occur whenever the temperature is below freezing, because as we'll see later, almost all the temperatures are below freezing. So I use the same method for shear and pair. The only difference in my methods is that I use different features for each one. Also, not only do I use different methods different features between pair and shear, but because in shear there are 2 situations, one set of files that has 3 nanometers and one set of files that has 2 nanometers wind sensors, that means that I have to further break up and have 2 sets of features for both of those, although they're going to be similar but slightly different. So the first step is I remove icing, and all steps after that assume that you've already removed icing and you ignore any time step that has icing. Then I'm going to split up the test data, and I'm going to associate every test file with its closest training file. I'm going to measure the distance, and I'm going to find its closest training file. Initially, I compared each test file to all the training files, but later on I refined that. Then I'm going to talk about weighting the features, and I'm also going to talk about specifically what features I chose. Then I'm going to talk about finding the threshold using training data, and then finally applying the threshold. So the first step is I made the hypothesis that basically the wind animators are heated. And basically the way the wind sensor works is it has 3 cups. As you saw on the first slide, it has 3 cups, and they catch the wind and it rotates. As it rotates, it measures the wind speed. So there actually are heated animators, and I read about this. And in fact, you need heated anemometers in this situation. And I was going to talk about it later. Not only do you need them, but they must have them, or else there'd be a lot more icing than what we see. So basically, the portion of the time, in other words, the time steps, so one file might have parts that are above or below freezing, is about 70% in all the files. So it's quite substantial. It's very harsh conditions, but this is what you'd expect because the highest wind speeds are found in some of the coldest regions. So if you look here, everything that's blue is actually below freezing, and everything that's green is above freezing. And not only that, but this is also a pair training file. So that means that this is, so you're not going to see any wind error except if there was icing, but as you can see here, there's really no icing. And later on, I'm going to show you a file with icing. That this part doesn't really look different from this. So that's another thing supporting the heated sensor hypothesis. So how do I detect icing? On the next slide, I'm going to show you what I think icing looks like. Well, first it has to be below freezing, but that doesn't really cut down the selection very much. What really cuts down the selection is when one of the wind sensors has stopped moving. And you know this by looking at when the standard deviation for the wind speed is 0. And also, since icing before a sensor freezes still and after a sensor freezes still, I think it's reasonable to assume that the sensor has been slowed down by ice accumulation. And so I'm also going to say that 1 hour before and after an obvious icing event, I'm also going to say icing has occurred. That there could, because I don't want to measure that region as not having icing and then find an error there and say the sensor's an error when it turns out it's really just icing. So that's why I do that. So here, this is with pairs, so there are two sensors at the same altitude. You can see how the second sensor has experienced icing and stopped, whereas this one hasn't. So just to give you an idea of what it looked like, and I looked through the training data and all the files, and this is sort of what I saw, and this pattern repeats itself.
So this is measured wind speed on the training data?
Yeah, this is the mean wind speed. And also, so not only is the second sensor considered to have iced, but also the first sensor, because if there are icing conditions for the second sensor, if that's iced over, then the first sensor is probably also iced over. Yes?
So how close are these wind sensors?
Oh, they're at the same altitude.
No, they're at the same altitude.
Yeah.
Are they at the same area?
Well, they're each on 10-foot outriggers, but the outriggers aren't completely. I think they're like 90 degrees to each other. So yeah, they're pretty close to each other.
Okay.
Yeah.
Is your time step in seconds?
Oh no, time step is in 10 minutes. Oh, if you look back previously, well, I won't go back. I'll just tell you. So the training files have 25 days worth of data. So that's pretty long, and the test files only have 5 days worth of data. So that's what this is. So each of these is a 10-minute interval. Wait. Oh, sorry. Yes, we are on this slide. What's going on? So this is just to give you an idea of, after I ran the algorithm I described previously, how much icing I found. So as you can see here, in the pair train, all of it's below 10% icing. And that's important because when I showed you earlier is that freezing temperatures occur 70% of the time. So going on, you can sort of see is a similar thing in pair tests. However, you see some really abnormal icing here. And well, I guess I can talk about it now. One sort of potential limit, there's really no way to know how well what were sort of the performance bottlenecks in my algorithm. Did I just go back? There's no way to know what were the performance bottlenecks in my algorithm because they don't give you sort of very good feedback. They only really tell you your rank. So one potential thing that could have degraded my ranking was how I chose to do icing. I do believe that when it's frozen still and when it's below temperature, that it's probably experiencing icing. And I'm not sure how else you could measure icing, but I think there's probably room for improvement there. And you see here the shear train, again below 10%, and you see the same pattern with the shear test, with the test data. So the next step is to assign each test file to one training file. And so I look at the distance, and the way I do that is I basically look at the percent difference in the wind speeds and also in the heights. And the heights are important because later on I'm going to incorporate heights into some of the features. So here you can see how basically how they're distributed, and also you can notice one of the training files is not used. Apparently, all the test files were closer to some other training file, and then actually in the shear example, all of the training files are used, and you can actually see that some aren't used very much. So the next step is to weight the features. So I'm going to talk about the features in a second. But basically the idea is you have a bunch of features and they're in the same units, and you want to basically decide which ones are important. And you could arbitrarily decide which ones you think intuitively are important, but I chose to instead use an algorithmic way to decide to see which one was most important. And so what I do is I take the dot product of the feature weights, proposed feature weights, and then I multiply that by the features. And when I mean the features, I'm looking at the training data. So the way it works is each time step, each 10-minute interval has a sort of a distance to the previous time step, right? How much the weather has changed in that 10-minute interval. And then what I do is I look at those distances, which are features, which I'll talk about later, and I multiply each of those times its associated feature weight. And then if the distance is small, and that's consistently small, and then what I do is I multiply the feature weights times that distance, and I do it for the entire file, all the distances, and all the training files, or in that one training file that's associated with the test file. And basically I'm trying to look for feature weights that are going to minimize that. And if it minimizes this dot product, what that means is you have feature weights that are weighting features that are, I guess, most important. And so anyway, so I typically every night I would run the simulation overnight for 1,000 iterations, but actually for this presentation I ran it for 3,000 for the final presentation or results. So here you can see well anyway, let me describe what this is showing. So this is over the 3,000 iterations, and what I did is I sort of wanted to show that my simulated annealing was doing something productive. And so what I did is if you're looking at the feature weights, initially the feature weights are perfectly evenly distributed. And then as the algorithm progresses, you should get a situation where some of the features are more important or some of them are less important. So you can see how far it's progressing in that if you take every feature weight, square it, and then sum those squares. And so that's what this value is here. This is the sum of the squares. And so it's increasing, which shows that the simulated annealing is getting somewhere. You see this here. I'm not quite sure what that is. And you see the similar thing with the shear 3, which is a shear situation with 3 sensors, and you see the same thing with the shear with 4 sensors. And also, if you're looking at the scales, the reason these sort of numbers are different is because pair has the least number of features, shear 3 has the next least, and shear 4 has the most. So the first set of features for pair and shear are, I call them vanilla features because they're very basic and easy to compute. And what they are is I just look at how quickly the wind speed changes. So for example, with pair, I'm looking at how quickly the mean standard deviation max and min of the wind speed changes. And the reasoning being is that if a wind sensor fails, then you're going to see an alteration from that. But that's a very basic, and one disadvantage of that is it looks at each sensor individually, but it doesn't actually sort of compare the information between them. So you may have a situation where in shear, for example, where suddenly the wind picks up, and then all the sensors increase really quickly. Right? And so you also want to have some sort of feature that can account for that can look at the difference in the wind speed between the wind sensors. And I'm going to get to that in a second. Oh, well, these are the non-vanilla pair features. So in my first iteration of the pair algorithm before this, I sort of made the assumption that if there's an error in the pair algorithm, if the two sensors are at the same altitude, then one should go a lot faster, then they should go about the same speed. So if one is going slower than the other one, then that means that it's having an error because at that point I assumed that an error caused the wind sensor to slow down. However, then later on I realized that might not actually be a reasonable assumption, and in fact I should make two different hypotheses. One is that if there's an error, the wind sensor will slow down, and one is that if there's an error, the wind sensor will speed up. And that could possibly happen if something's on there to sort of increase the resistance of it. If that breaks or something, then it could go faster. So so you have this problem, right, where you have two sensors, and say this is now keep in mind, for pair, I look at each sensor individually, and I'm saying, is this sensor in fault? And then I look at the other sensor in another run of the program, is this sensor in fault? So we're talking about, let's say we're talking about sensor A right now. We're trying to determine whether it's at fault, right? And sensor B is the other sensor that you have. So what you do is sensor A is faster than sensor B in this situation. So you have one measurement of how much faster, what percent difference, how much faster is sensor A than B. That's one measurement. But then you have another thing, which is how much slower is A than B. Right? So it's not really slower than it. So you have to come up with some number. And so I decided to double the difference, and that's how far it would take to get below it. You can't, the problem is because of the step I talked about previously, because stuff I talked about previously. Where is it? Here, the stuff I'm going to talk about previously, we're talking about the features, that distance, right? So if we have how much faster, this is how much faster it is. So to get how much slower it is, because it's not slower, that means it's not a real significant feature, right? And because it's not a real significant feature, that means we want to give it a greater sort of distance to discount it, and so that's why we double it. That's why we do that. So, okay, pair. This is a percent function difference I use, function I used. So now onto the non-vanilla shear features. Now the idea here is you want to look at, again, I mentioned it earlier, you have two wind sensors at different altitudes, and you want to look at their difference in wind speed, how much that changes. The idea being that, I talked previously about how the wind gradient idea didn't work. But this is different because even though the wind gradient might not be faster up here than it is here, it's at some point in time because of sort of disturbances in the ground, for example, certain terrain, one is going to be sort of consistently faster than the other one for at least some period of time before it switches. And so that's what this implements. And so what I do is I look at the difference between this sensor and this sensor, and then I look at how that difference has varied from the difference previously. And the idea there is that if what I mentioned earlier, if the wind speed picks up, then you'd expect the difference to stay about the same. However, since there are three sensors, you have to compare all the possible pairs. And with the 4 sensors, you again have to compare all the possible pairs. And that's why that's one of the reasons why shear 3 and shear 4 are going to have a different number of features. So basically, all these colorings here are just so you can read the graph a little bit easier because there's a lot of bars and it's kind of hard to read. So these first 4 are the vanilla features, and this is for pair, and that's because there are 4 different statistics for pair. There are wind statistics, and you're measuring how quickly they change. And then 5 through 12 are the non-vanilla. And if you remember, one of them is measuring with the A and the B. One of them is measuring how much faster the wind sensor is, and one of them is measuring how much slower. And so the even are how much. I guess the even are how much slower it is, and then the odd are how much greater. Although really the order is arbitrary. But then this is for the mean, the standard deviation, the max, and the min. And looking at this, it's really hard to see a pattern that's intuitive. That simplifies it. Yes?
So these weights are obtained through your
simulated annealing, yes. And this is for the shear, and this goes up to 12 because there are 3 sensors, and each one has 4 statistics, and you're measuring how quickly those change. And so this is the vanilla. And then for here, you have 3 possible. This is showing that difference, right? And for each of those, you have 3 different sensors, right? And so you have 3 different possible pairs of them. And order doesn't matter in that scenario. And then for each of those, and that's where you get the 3 here, and then for each of those pairs, you're measuring a different statistic, right? Mean, min, max, or standard deviation of the wind speed. And so that's why I have 4 bars here. And then for shear 4, it's similar with 16 vanilla because 4 sensors and 4 statistics, and the same reasoning for the non-vanilla. No point repeating myself. So the next step is finding and applying the threshold. So the first step is, so I have the weights that I found earlier, and then I apply those to the training data. And then once I've done that, I find the sort of the mean, I find the standard deviation, and then I find how many of those sort of distances after they've been weighted are beyond 1 standard deviation because it's not a normal distribution. And then I take that number, and then I then go to the test file that's associated with that training file, and I take its mean, and I take the mean of the training of the test file, and then I take the standard deviation of the training file, and I say how many times has it exceeded 0.9 standard deviations, and if it's exceeded it more times than the training file has, then there's an error. Now the thing about the 0.9 is on the last submission, I was thinking maybe I can increase my score. Maybe I'm not measuring enough errors. And so I thought I would actually increase the number of errors by putting 0.9 here. But actually, when I looked at the ranking, it looked like I actually dropped a little bit because of that. So that probably wasn't the wisest thing to do. If I'd had time, then maybe it does make sense to multiply it by something, but there should be a more algorithmic way to determine that. But that was something that was tacked on at the end. So the pair results are basically there's a lot of situations where both sensors fail. And I think that sort of seems reasonable. If there are very high winds or there's ice that's going to freeze it and then rip it off or something, then you're going to see something like this, because similar conditions will probably ruin the similar sensors basically. And shear, there's a lot of failure. And so, sort of generalizing this, I think this could be generalized to other domains where you want to determine sensor error. However, I'm sure it probably has already been generalized. It's not really something that's easy to search for, because I'm not really sure what you would call it or what terms you would use to search. So I'm not sure how this is, if anybody else has implemented something like this in some other thing, but they probably have. So I was down here as my final ranking. Aeolus, the Greek god of wind. So any questions?
I think in summary, you identified how many sensor faults in general. I can go back to your previous slide, just try to highlight. So
that's shear.
Okay, for the shear. So there are only like 57 no failure testing examples, right?
Yeah, yeah.
And overall, if all you declared sensor faults are correct, your score would be like 400 or 500 something.
Oh, one point. These numbers don't mean anything. They've been obfuscated. They don't tell you how they've been obfuscated.
Yeah.
The rank is all that matters. The numbers are meaningless.
Yeah, but the score means at least with a subset of the testing samples.
Where did you see that?
Well, I think that's in some discussion forum or actually in some announcement.
I hadn't seen that, but if that's the case, okay.
Anyway, that's an indication on roughly how many sensor faults you would expect to be. But of course, you don't have any penalty for declaring more sensor faults in the current scoring system. But in my opinion, you should.
Yeah. Yes, Zach?
How were your ideas submitted to PHM? I'm just curious. Like, how did you submit them
so with the shear, there are 2 possibilities, and with the pair, there are 4 possibilities, 0 through 3. And so I look at all the test files, and so I have basically a username and a password, and then all my answers, I think, for the pair, and then all the answers for the shear, and that just submits as a text file by email. It's kind of primitive.
So 0 through 1 are, what do the numbers mean?
Oh, 0 means no failure in shear, and 1 means failure.
So those tables that you had, was that something they had up, or is that something you
What,
found?
this?
Yeah.
Oh, this is just from my output. Like, no, they don't say. I don't say no sensors. No, this is just like I went through my file and I said, so how many zeros do I have? That's here. How many ones do I have? How many 2s, how many 3s? Yeah.
That's just a summary of the result. But it's an indication of like how many sensor faults you declare, or maybe in this case specifically whether it's a sensor 1 fault or sensor 2 fault or both.
No, that helps. Okay. Thanks.
Any other questions?
And you said the final result is like, because I think I also submitted a couple of entries.
I was above you. I was above you until I added that 0.9 thing, which brought me down.
Okay, but is this your final submission or this is?
Yeah, this is the final submission.
No,
yeah,
I don't
the 11th.
think so. I think this is updated yesterday. I think.
The 11th was the last submission.
No, I would say 11. Yeah, but this is updated on July 11th. I think today is like probably the final announcement.
Oh, but the actual final submission they sent out an email was yesterday.
Well, it ended yesterday.
Yeah.
Yeah, but you can still submit yesterday, and this might not reflect the final update. But I do realize that I think the student with the alias DSUC was on top for quite some time. And
yeah, I think probably what happened is people basically I don't think that the actual order changed too much. I think basically people had some algorithms and they either worked or didn't, and they fine-tuned them. Yeah.
I still don't see what might be the diagnostic features in this particular example, because it seems that, at least in my opinion, you're declaring too many sensor faults compared with, which I don't know the actual number, but I would make a guess somewhere below 200.
Yeah, I know I am probably declaring because I added that 0.9 thing, which reduces the threshold. So I guess I probably am declaring too many, but that would be easy to change.
Did you do any research on the hardware itself, on the sensors itself maybe?
Yeah, I did. That's how I knew they were heated sensors, and I tried to look for sort of what caused them to fail, and it looked like it was probably like either a cup would come off, which would cause it to slow. I didn't really find anything that would cause it to speed up, but I figured I don't need to make that assumption. I can let the program figure it out for myself. So I added that thing into pair that didn't make that assumption. So yeah, I did. That's how I knew heat sensors existed.
I figured there'd be like a data sheet with some specifications to it that says after that sort of like the productive.
They didn't tell us what. They gave us very little information. They didn't tell us what type of sensors they were using.
The problem is that we don't have any single example telling you that's an indication of sensor fault.
Yeah.
You only have the training samples, like no sensor operating at normal.
They only gave us the data that was basically in the files. Anything else, like what type of failures they could have, was something you had to come up with yourself.
They probably didn't give you a major model or anything, because if you could like hypothesize what it more or less was, you can get at least an idea of where they.
Well, I already know it's a heated sensor, and I already know it probably has 3 cups.
Yeah.
And knowing the make and model probably wouldn't help me that much. What would help is if I knew the location where they were and the humidity, because I think humidity is tightly tied with icing.
Yeah. Also, you said something about there was data, the dates of the data that you disregarded.
Yeah, I didn't see how that, because I thought that the information there would basically be reflected as wind speeds and temperature. And so I didn't think it could really be useful. And you could use it for humidity, but I didn't know where it was, and so that isn't useful.
Yeah, but I mean, the date was it like throughout the year or?
Well, no, I didn't look at that. I didn't see how it would be. How could you use it? What do you think you could use it for?
Well, if it's during winter, then there's more inclined for icing.
Yeah, but the critical thing about winter is it's cold, and we already know it's cold, so it doesn't give you any extra information, and it doesn't tell you the humidity. You know what I mean? It doesn't help you.
Well, I mean, it might just. You can argue either way, I guess. I don't know. Because you don't know where the location is. So, because if it was like, I guess in Siberia versus, Florida, there's a big difference.
Well, but it can't be in Florida because it's
I suspect
temperature.
it's somewhere collected, maybe in Colorado, some places. Probably I think having this wind harvesting for alternative energy is an important aspect for this type of prognostic applications.
Yes.
Oh, I was gonna play on that and say, like, could you account for like a seasonal change? Like if you know it's over so long that you know the temperature would change no matter where it is.
I didn't look at seasonal changes. I still don't see how that would help you.
Because some places have rainy seasons or more humid seasons, so maybe you could look for a distinct trend over time.
A distinct trend, but how would I? But if I don't know where it is, like keep in mind you don't know where it is.
Well, I know. I mean, you don't have to. I mean, it tends to do something if there are certain statistics in one time period as opposed to like at the beginning, and it has different statistical features towards the end.
You can still look through.
I think I cover that by associating the test file with its closest training file. I don't really see what you get, Zach.
Well, I think what Joe's trying to say is that you could look at the data and see how certain trends happen over time, and you could see similar things happening in the same training file, not just marking them to test files, but actually seeing, like, here we have a lot of icing occurring because maybe humidity's high. Then it doesn't.
You don't have humidity. All you see is icing. I'm just saying.
No, I'm not saying that there's humidity in the file. I'm saying that there's.
You're looking at just the numbers.
You're just looking at just the numbers.
With respect to time.
And you see maybe there's a lot of icing here. Then for a while there's almost no icing at all, and then it speeds up again. It could be a seasonal change in how the humidity is working or weather.
That can't be a seasonal change because the training files are only over 25 days, and each
Okay, well,
test
that
file.
Well, okay, then.
I forgot that part.
Yeah. Okay.
Do you know like which 25 days relative to one another?
Well, only in the shear they give you that. In the pair they don't. They don't give you the dates in the pair.
And also, there are some possible file corruptions within the data file. Like there are some non-applicable data and some other misassociated entries in the training and the testing files. So I don't know how they're going to handle that. But basically, these are also some examples you have to say whether there's a sensor fault or not. I usually just say because I don't know, so I can only declare there's no fault. on the sensor because you don't give me the adequate information for me to make a judgment.
Yeah.
But the current scoring system encourages you to declare more faults because there's no absolute penalty on declaring more sensors.
Well, there is for pair, but not for shear. Because for pair, there are 4 possibilities, and if
Yeah.
you don't, and if you say they're all sensor.
Yeah, but
they're-
still, I mean, within 1, 2, and 3, there's a chance you guess it
No.
correctly.
No. But if you say there are 2 sensor faults and there's only 1, you get no points.
Yeah, but what I'm saying is, if you say 0, then of course you don't get any. If you're wrong, you don't get any score. But what I'm saying is, if you make an educated guess, either 1 or 2 or 3,
No,
there's
if
a chance you can still get something.
I think you get a point if there are 0. Well, that's something I didn't really look at exploiting, because if I had wanted to exploit the scoring function, I would have just said all the shear is wrong. But of course, you can't do that because then you'd be considered cheating, and you couldn't really go to the conference because your method is exploiting the system, and it's not something they'd accept. So.
But of course, in any method, if you adjust the threshold, there's a tendency you may want to declare more sensor faults than it should be, because of if you just want to improve the score.
Yeah. Okay.
Okay, so thank you very much. Okay, so I guess that concludes the final presentation. I would like all of you to submit your evaluation sheet